And you are of course most welcome. This is Project Euler problem number 27. Quadratic primes. Euler discovered the remarkable quadratic formula n squared plus n plus 41. It turns out that this formula will produce 40 primes for the consecutive integer values of 0 to 39 for n. So if you plug in 0 for n, you get 41, which is prime. You plug in 1 for n, you get 43, which is prime. Plug in 2 for n, you get 47. 47, which is also prime. You keep doing this up till n equals 39, you always get primes. That's extraordinary. Anyway, the incredible formula n squared minus 79 plus 1601 was discovered, which produces 80 primes for the consecutive values 0 to 79 for n. Now the product of the coefficients minus 79 and 1601 is minus 126,479. Now considering quadratics of the form n squared plus an plus b, where a can be anything between 999 and minus 999, and b can be anything between plus and minus 1000, find the product of the coefficients a and b for the quadratic expression that produces the maximum number of primes for consecutive values of n starting with n equals 0. Okay, so I'm going to show you 3 solutions today, each one building on the last in some way. We'll start with the brute force method. So we're going to need is prime. So from SymPy import is prime. You can of course download an is prime function off Tinternet if you want. I'm just going to use the built-in one. So the brute force method, we're just going to go through every possible value for a and b, generate all the quadratic results, and then see which is the biggest run of primes for n. So I'm going to have this as a function. So def p27 slow, doesn't need that. Okay, best run equals 0. 0. Best product equals 0. And then for a in range, now a can go from minus 999 up to positive 999. Python's bloody awkward, so we write it like that. And then for b in range, minus 1000 up to 1000. Bloody Python. So that's done. And then n equals 0. We just keep testing the quadratic until we find a value for n which does not produce a prime. So while is prime, a squared plus, it's n squared plus a times n plus b. N plus equals 1, we just keep counting up for n, and then when we come out of that loop, we then need to compare the current n to the best run. So if n is bigger than best run equals n, and best product equals a times b. And that is pretty much all we need, I think. I'm going to time this as well. From time import perf counter. Right, so start equals perf counter, and then end equals perf counter, and then print. We want to print the best product and end minus start. Okay, so we are going to run p27 slow and see how that performs. So I'm going to get rid of the Chrome so you can see the result. There we go. And hopefully I've got this right. It looks okay. Take a couple. Oh, didn't like that. Okay, didn't like the didn't like the indent, because Python is fussy as hell. There we go. It is running. Just takes a few seconds. There we go. That is the correct answer, and that took 8.47 seconds. So that is quite slow. Okay, so a slightly better solution. There is actually a clue in the oh, I should bring it up, shouldn't I? Excuse me a second. Right, there is a clue in the problem definition. This one up here, n squared plus n plus 41. Remember that our equation is n squared plus an plus b. And we always start with n equals 0. So when n equals 0, this disappears, the n squared, the an disappears, and we're just left with b. So in order to produce a prime on the first run, b has got to be prime. And we see in the example n squared plus n plus 41, well, 41 is prime. I believe 1601 must also be prime. So instead of looping through all the values for b, we can just find all the primes between -1000 and 1000 and use those. That could be a bit quicker, couldn't it? So we're going to use a sieve to find the primes, and I've got one in, I did one in episode 7. This is the sieve of Eratosthenes. I'm not going to go through the algorithm again because it's quite lengthy. I'm just going to copy the code. So that's a sieve of Eratosthenes. Okay. I wonder if you can actually hide lines of code. One day I'll figure out how to do that. Anyway, def p27 faster. So again, we want a perf counter. So we do want best run and best product set to 0. But now we're going to get the values for b, which is going to be a sieve. So sieve of b equals sieve up to 1000. Now b is going to be a list comprehension, and it's actually going to be a list of lists, if that makes sense. So b equals I and minus I for I in range 2 to 1000 if sieve of b I equals true. Okay, so basically this sieve produces a list of booleans, true or false, determining whether the index is true or is prime or not. So 2 would return true, 4 would return false, and 197 would, I think, return false. So that's that, and then we've got b. B is a list of lists. I will actually show you the output so that you know what I'm talking about. So I will get rid of Chrome so you can see what this is doing. Okay, so we have a list of lists here with the positive prime and its negative corresponding values. So there we are. That's all working. Right, so next thing, oh, what's that doing down there? Anyway, next thing to do is generate all the answers. So I'm going to copy, no, I'm not going to copy that because this is going to be different. For A in range, so A is still within the same range, -999 up to 1000. And then now this is a list of lists, so we want to loop through both values within the inner list. So for B1 in B and for B2 in B1, n equals 0, while, and I will actually copy this because it's the same code, just with a few minor changes. There we go, that's not indented properly. Why does it not do that? That needs to indent. That needs to indent, and that needs to indent. Change that to B2. Change that to B2. And then right over here, end equals perf counter, and print best product end minus start. Right, that should work. So let's see how quickly this goes. Same answer, and now it's 2.89 seconds. So we've got it down quite well, but I think we can do better than this. We can actually get this down to, I think, less than a tenth of a second. So I will get a drink and then we'll return and have a look at that. Okay, so this bit's going to be a little bit tricky to explain. There is another clue. Now I did say that b in our equation, the free term, has to be prime. If you look at these two equations, you will see that there is another clue hidden very, very deep. Now, I went on the internet and I found this. This is a Wikipedia article called Formula for Primes. We're going to go to section 7, Prime Formulas and Polynomial Functions. Now, there's a bit of mathematics gumph up here, but we learn, there's the equation that we know. There it is. So let's read on a little bit. So, the phenomenon is related to the Ulam spiral, which is also implicitly quadratic, and the class number. This polynomial is related to the Heegner number 163 equals 4 times 41, there's 41, minus 1. So what has 163 got to do with our equation? Well, let's have a look. Now, a little primer on quadratics for those who don't know. And I barely understand this myself, so bear with me. So here is a graph, a very shitty graph. Now we can plot a quadratic equation going through the graph like this. Now some of them will cross the x-axis in two places, such as this one. Some quadratic equations will only touch the x-axis in one place. We call this equal roots. Some graphs will never touch the x-axis, and we call this no real roots. Now there is a formula called the quadratic formula that tells you where on the x-axis the quadratic equation will cross and how many times it will cross. This equation is minus b plus or minus the square root of b squared minus 4ac divided by 2a. Now the bit that tells you how many times the graph will cross is called the discriminant, and it is here underneath the square root sign. B squared minus 4ac. Now let's have a look at the equation we've examined so far. N squared plus n plus 41. How many times does that cross the x-axis? Well, we can plug some values into the quadratic formula, specifically the discriminant. So let's do that. Now, this is going to be a bit tricky because we're mixing up our a's, b's and c's here, but for the purposes of this demonstration, a is the coefficient of n squared. A is 1. B is the coefficient of n, and C is the free term, 41. Let's feed those into the formula. So 1 squared minus 4 times 1 times 41. That is 1 minus 164, which is, bless my soul, minus 163. What about the other equation that was on the same page? Let's have a look at that. What was that again? Let's go over to that page. There we are. It was n squared minus 79n plus 1601. Okay, let's plug those values in and see what we get. So I will get rid of Chrome. So this time, excuse me, this time A equals 1, B equals, was it 79 or minus 79? Minus 79. And C equals 1601. So we have minus 79 squared minus 4 times 1601. Okay, now minus 79 squared is 6241 minus 6404, which is minus 163. So it's pretty obvious that when the discriminant is minus 163, we are going to produce a very long run of primes. So once we have got a value for b, which of course must be prime, we can then find a corresponding value for a. So let's take an equation, like let's take the quadratic formula and rearrange it. So we know the discriminant has to be minus 163, and we know the equation is b squared minus 4ac. I'm going to have to rearrange this slightly because our equation is slightly different. We have an a, so this is a and this is b, and this is always 1. So this is going to be slightly different. I'm going to rearrange this into something that fits our equation. So that's going to be a squared minus 4b. So we know what b is going to be. It's going to be a prime number. So we need to rearrange this equation in terms of a. So let's isolate a, and we are left with minus 4b plus, no, sorry, I'm not very good at algebra. Minus 163 plus 4b equals a squared. And then we have to take the square root of both sides. So it's the square root of minus 163 plus 4b equals a. So this is the equation we use to find a. So what we're going to do is find all the primes within the range for b, and then find all the corresponding values for a and loop over those. It's going to be a much smaller solution space. So I will tidy this up and then we will have a go. Okay, so there is something else I noticed here. This square root sign. Now obviously you can't have the square root of a negative number, so b has got to be positive and it's got to be at least 41, which is fine because we knew that 41 was kind of an important number, so we will start there. So we're going to filter out all the primes from 41 and up. We're going to find the corresponding value for A, which could still be positive or negative. And then we're going to build a list of candidate pairs and then test them with n and see what we get. So that goes. And let's begin. Def P27 fastest. There we go. So these 4 lines of code pretty much don't change. I will change a little bit. Let's move this right to the top. There we go. Right, that has got to be 41. And now we only want the positive value for I, so that changes to that. Right. Now we find the candidate pairs. So what are we going to do? Oh yes, for value in B, discriminant equals minus 163 plus 4 times B, and it's going to be the square root of that. Now obviously this has to be an integer because A can only be an integer, so we have to do a check. So if discriminant minus int discriminant equals 0, then we know it's an integer. In other words, if there's no fractional part, we know it's an integer. So then we add it to the list of candidate pairs. So pairs dot append. Now A will be the discriminant and B will be the current value, so value there. We also want the negative value for the discriminant, so we'll just copy this line and have negative discriminant. Oh yes, but we must convert it to an integer just to make absolutely sure, because this here will give a floating point value which we don't want. We want the integer value, so let's do that. There, right, so we're cooking with gas now. So for pair in pairs, n equals 0. So while, and this is following the same code as previously, so while pair, why don't I try something else for A, B in pairs? I wonder if that would work. While is prime n squared plus A times n plus B. It's not throwing up an error, so that's okay. For A, B in pairs, while is prime all that, n plus equals 1, then at the end, if n is bigger than best run equals n, and best product equals A times B, and then we print off best product. Oh, we need the counter as well, so end equals perf counter print best product. I think we're almost done. So let's call the functions, starting with P27. What was it? P27 slow, faster and fastest. P27 fastest. Get this done. Right. Moment of truth. Seven seconds. Oh, didn't like it. int and list. Oh, its value. Oh, blimey. Okay. Well, we can see that 7 seconds and 2 seconds. Let's just try the last one. Let's not waste any time. Let's just get on with it. Boom. Oh, it didn't do the end counter. Let's go. And there we are. So that has printed off 0.007 seconds, less than a hundredth of a second. So that is it for problem number 27. Thank you very much.